Hi, I'm Kayla Stajkovic, and I'm going to talk a little bit about HLM. So if you've ever worked with real organizational data, you already know this is a problem, even if you haven't named it yet. Most social science data is nested, but a lot of our analyses quietly pretend that it isn't. Think about the kinds of data that we study in management. We have employees who are often nested within teams, and then we have teams that are nested within organizations. And we also have the same person having repeated observations over time. The problem is that traditional regression analysis has this assumption that all observations are independent and equally informative, but in reality, that's rarely true. It would be like pretending that students exist independently of their classroom, as if the teacher, the school, and the shared environment simply don't matter at all. We know that's not the case. So the real question becomes, how can we analyze the data and also represent where it came from? And at a conceptual level, this is exactly what hierarchical linear modeling, or HLM, is designed to do. So most of the time, when we try to understand people, we are really studying them within groups, whether we realize it or not. So to take the classroom example, let's say we have students who are different from one another, but they're also shaped by the classroom that they're in. So students might be equally capable, but imagine a class that has more support, better resources, better teaching style versus kind of a chaotic, less supportive environment. And if we ignore the differences in the classroom and we just compare these students, we might draw the wrong conclusions about why somebody is struggling or doing well. So we need a way that we can understand both things at once: how people within a group differ, but then also how the groups differ themselves. And so this is what hierarchical linear modeling is designed to do. It's a way of analyzing data by explicitly acknowledging this nested structure, that there are these groups that surround people and that affects people at the individual level, and data exists at more than one level at the same time. So HLM allows us to do two things simultaneously. First, we capture this within unit or within group differences among individuals. And then second, we're able to capture the between unit or between group variation, those differences among teams and organizations. So what HLM doesn't do is it does not collapse everything into a single average effect. So instead of forcing everybody into the same model, HLM allows different groups to have their own starting points or baselines, also their own slopes, and it enables us still to estimate that overall average effect that we care about. So we're not ignoring individual differences and we are not ignoring group context. Instead, we're modeling both at the same time. One important clarification is when people talk about HLM today, they're usually referring to a family of tools that are used to model nested data. So depending on your discipline, your software, tradition, your training, these tools might look a little bit different. You might hear HLM described under different names, things like multi-level models, mixed models, random effects models. These are all ways of addressing the same core issue, which is nested data. In my own research, I use something called linear mixed effects models. I know the terminology, it might sound intimidating, but the underlying logic is actually very intuitive. What a linear mixed effect model does is it separates effects into two groups. We have the fixed effects that we use to answer the question, what is the average relationship that we care about? What do we want to generalize beyond context? And then we have the random effects that answer how much of that relationship or baseline level varies across contexts. Now, I do want to say a word about this label of random because I feel like it's a little bit misleading, because the effects in this group are not random in the way that we think about the everyday sense of the word. They actually represent systematic differences across people, teams, or settings. Another key point here is we're not usually interested in interpreting random effects themselves. Instead, we're including them to parse them out to give us this cleaner, more precise estimate of our fixed effect, which is what we're interested in. But if we ignore the contextual variation and we don't model the random effects, that can lead to a misspecified, overconfident fixed effect. So importantly, random effects are not about complexity. They're about protecting the effect we care about and getting the most precise and accurate estimate of that as possible. So for example, a fixed effect might ask, does leadership predict performance on average? What the random effect is going to do in that model is tell us, like, do teams start at different performance levels? Or are some teams affected by certain leadership styles more strongly than others? And that distinction matters because, again, it's not complicating the model. That's not the point. It's about making the model more honest so we can really get to, like, that true leadership effect. And that's the heart of the issue. So this is really important. If we don't separate the fixed effects and the random effects, we risk attributing the group level differences to the individual level relationships. Said differently, if we ignore the nested structure of data, a few things are going to happen. We're going to get underestimated standard errors. Our fixed effects are going to look stronger than they really are, and our results are likely going to appear more statistically significant than they should be. So this is going to lead to inflated confidence, biased conclusions, and theory claims that don't replicate well. Here's an intuitive way to think about it. Imagine that you're evaluating runners in a race, but you don't account for the conditions that they ran in. So they ran the same distance and the same rules, but some runners ran in a headwind, others had a tailwind, some ran on hot days, others ran during rainy days. And if you ignore those conditions and those differences and you attribute the performance differences to ability alone, you're not really presenting an accurate picture of what happens because we know context mattered. That's what happens when we ignore the nested structure of data. So what HLMs do is they allow us to more accurately look at this fixed effect that we care about by accounting for the structure of the data. So we're not removing variability, we're actually explaining it better. And this distinction, it has real consequences. So theory-wise, we're getting cleaner estimates, better tests of cross-level hypotheses, and fewer false positives that are going to kind of clutter the literature. For practice, more realistic predictions, better leadership and policy recommendations, fewer like one-size-fits-all conclusions, and because the effects that we're interested in are often at one level, but there's variation at the other, we're getting that more precise estimate because HLMs respect that reality. So at its core, HLM is not really about statistics. It's about the structure of real world data. And so linear mixed effects models give us a way to do that without pretending that the world is somehow flat when we know that it's not.